Hello everybody, and welcome to another lecture on computer architecture. Today I want to talk to you about de Morgan's laws. And de Morgan's laws are actually quite interesting and powerful tool for our design in digital systems and computer architecture in general. So what is this all about? Well, we have to go back to Mr. Aristotle, when with his categories he explained the logic of things. And then Mr. Boole and Mr. Huntington and Mr. De Morgan, they invented then the mathematical rules for that to formalize it in a way that you can work with it mathematically. But the ideas all came back from Aristotle. So let me show you what this means. So let me put here, I want a vertical. So what do I have here? I want, for instance, I say I take my umbrella when it is raining and I go for a walk. So this is we have here an AND logic. So if it's rain and walk, and we put this into, well, let's put it already in some kind of formal logic circuit. Let's call this the AND operation. And then when it's raining and I go for a walk, then I will take my umbrella. So what do I want? When do I not take an umbrella? I want to know, to find out formally, without doing much Aristotelian logic. I want to know when I do not take an umbrella. So that would be the negation of this AND operation. And then in comes Mr. De Morgan, because he says that basically, to remember it, I will say it like this, that the negation of a product is the sum of negations. Negation of a product is the sum of negations. And we already know that for the product, actually we should read an AND operation. And for a sum, we should read the OR operation. So actually what we're saying is the negation of an AND is the OR of the negations. In this case then, of course I already know this, that when do I not take an umbrella? So umbrella, I put it here, when do I not take an umbrella is the inversion of this one. So what it is saying that the OR, then I put it like this, the OR of the negations, not rain, not walk. So I will not take my umbrella if it is not raining or if I'm not walking. So you get the idea. If I have the umbrella, I take the umbrella if it's raining and I go for a walk. And I will not take my umbrella, that's negation. So I have to negate this product. So what I will do, I will negate the entrances of my gate. And instead of an AND gate, I use an OR gate. So I can also put it like this. This circle represents negation, and this one then becomes the OR gate. I'm not sure, I'm not very good at drawing. So this is an OR gate, and here we all have not umbrella, and here we have rain, and here we have walk. So these circles now, they represent negation, and also this line here on top represent negation. What you should get from this is that the negation of a product is a sum of negation. The negation of an AND is the OR of the negations, and that we get here. Let's show this with a Venn diagram. What did I say? The negation of a product is a sum of negations. Or the negation of an AND is the OR of negations. Let's show it here. Now we have here this Venn diagram. You have here A and B, and of course the intersect of this one is A and B. That is the red zone which I show here. And then of course the negation of this is then the inversion of this zone. So that would be everything except this. So everything except the white zone here. That is not A and B. And now let's look at it if this is true, if De Morgan is right. So here we have not A, that is this green zone. Here we have not B, that is the green zone here. And then of course not A or not B is the green zone here. And as you can see, not A or not B is equal to not A and B. And you can do this also with 2 circles, you can do it with 3 circles, you can do this with as many circles as you want. In general, it is that the negation of a product, we write this like this, the negation of an AND with many inputs is the sum of negations, or that is to say, that is an OR of many negated inputs. So that is the rule which we call negation of a product is the sum of negations. And then the other one which we can have then also have, and this I will not show in Aristotelian logic, but just here with the Venn diagram, and that is that the negation of a sum is the product of negations, or the negation of an OR is the AND of the negations. So let me show this here. We have here the circle A, the circle B, and then of course A or B is the junction, the union of the 2 circles. And then the negation of that, not A or B, of course, is then the inverted areas. And that is shown here in red. Not A is shown here on the left in green. Then not B is shown here in the middle in green. And then of course the intersection of these 2, not A and not B, is actually shown here in green. And as you can see, it is equal to not A or B. In general, the second De Morgan law is the negation of a sum is a product of negations. You should read this once again as the negation of an OR is the ending of the negations. Or written in this way, the negation of a sum of input variables is the product of these input variables negated. Now, I would like to give you here an example. So let me go back to my drawing board here where I did this. Let me erase all this. So I want to just give you an example. Example, if we have the exclusive OR, that is this symbol, exclusive OR A, exclusive OR B. Later we will find out exactly what it is, but I can write you now that by definition this is A and not B, or not A and B. Yes, so what is the negation of this? The negation of not of A exclusive or B then is the negation of this entire thing together. Negation. And now we have the negation of a sum. Here we have the sum, or this OR, the negation of this. So that means that is the product of negations. So I have this one term and the other term, and I have to both negate them and make the product of that. That is A not B not, let me put this in brackets, multiplied, that is ended by not A and B negated. That is just the one that I'm reusing. The negation of a sum is the product of negations. That's exactly what I'm doing here. Now inside here we have now a negation of a product. So as we know, negation of a product is the sum of negations. So what we do here, we have to convert this one, the negation of this product, we have to convert into a sum of negations. So that is, let me put here the bracket, A negated plus B negated negated. And this one, we still have here the end, A negated negated plus B negated. And then we can actually know that the inversion of B, the inversion of B is B itself, and not A is A itself. So what we have here is not A plus B and A or not B. And now I will work out the cross terms. So this is not A plus not A and B. I should also put here every time when I write like this, of course there's an and in there. And I'll put this one and or B and A, or I should better write this A and B. As you know, you can invert this. That was one of the Huntington postulates. And or we have this or B and not B. And as you know, one of these Huntington postulates, let me see if I can show you this one. There we have it. Huntington postulate A, now I'm sitting in front of it I guess. A and not A, this is 0. Here we have 0. and B and not B, this is also 0. And then 0 or something is that something. 0 or something is that something. So that one, I can just cross out this one and I can cross out this one, and we remain with, let me put it also in this way, A and B, or not A and not B. So the exclusive OR negated actually becomes A and B, or not A and not B. This is just to give you an example of how you can work with this, De Morgan's laws. And finally, in this lecture, I want to point out something interesting to you, that many of these equalities that you have here that we derived, some of them they were directly given by Huntington postulates, here shown in orange. The other ones we derived based on that, so we're slowly building these laws that we are going to use. But we notice something funny when we look at this, that for every law that we have then the sister law or equivalent law. So if, for instance, look at this one, A and 0 equals 0, but we also have A or 1 equals 1. So it seems to us that every time when we find a law and we replace the AND operation by an OR operation, simultaneously every OR operation by an AND operation, every 0 by a 1 and every 1 by a 0, then we get another equivalent, we get the sister law. So in this case, A and 0 equals 0. So we replace the AND operation by an OR operation, the 0 by a 1, and then this 0 by a 1, and we get again a law. And for instance, let's see if we can do A or 0 equals 0, so that becomes A and 1 equals A, and that is this one, as we know. So this is something interesting. So that applies for whatever rule that we found. For instance, this one, A or A and B, that was a strange rule that we found, that the B can completely disappear from it. So we replace the plus here with a dot, and it becomes here. So that is, the OR operation becomes an AND operation, and the AND operation becomes an OR operation, and we also get rule that applies. And that is actually the case for every rule that we find. If we replace in this way AND for OR for AND, 0 for 1 and 1 for 0, then we get the equivalent rule, or the sister rule I should call it. So this concludes this lecture on De Morgan's law. What I told you is that the negation of a product is the sum of negations, and the negation of a sum is the product of negations. And then of course you should read a product is an AND operation and a sum is an OR operation, but that sounds much nicer to talk about products and sums. So that is actually classic jargon in informatics science. So I hope you enjoyed this lecture today.